Hello, in this video I will work out a simple problem of a shear strain, how to compute shear strain. Um, and this is a biological application. Um, this is the shear modulus of a spinal disc. You know, a spinal disc is stacked up, and when you bend, you apply force on one side of the disc. Uh, and this can model something like that. Okay, so here's a disc, a spinal disc, which we can kind of model as a 4 centimeter diameter, um, a cylindrical shape. We're not going to worry about how high it is because we are only interested in the angle it's going to make. Okay, so this angle is the shear strain. So that's what we're supposed to find. So this is the shear strain. Well, if I can figure out this force that I'm applying on this surface while keeping this surface fixed, that's when there's a torque around this point, and that's what it start to change shape, right? So this force divide the area of that upper part will give me the stress I'm applying. And this type of stress is shear stress. It's happening all through the body, okay? Because when it gets deformed, molecules are no longer in the same orientation to each other, and so they are applying different amount of force inside than what's the case in the equilibrium situation. So this additional force is causing force per unit area, which is the shear stress inside. And even if I don't know what's inside, just by knowing where the force is being applied over this area will give me the value of the shear stress. So shear stress here will be this force over this area. So stress is always force over area, but you got to recognize which force and which area for different types of shear, different type of stress. So this is 600 Newton. The area we're talking about is the pi, and because this is in regular SI units, and this is in centimeter, I need to convert that into meter, and that will be 0.02 meter square. Okay, I'm going to just say that this is 3. Okay, this is equal to 3 times 4 times 10 to the power minus 4 meters square, and this is 600 Newton. So I'll have unit Newton or meter square, which is same as Pascal. From here, this 2 cancels 1, and this makes it 50, and this will, when go up there, this 10 to the power 4. So this is like 5 times 10 to the power 5 Pascal. So that's how much shear stress is applying, right? The Hooke's law tells me how strain is related to stress. This is like a general formula. So this theta, which is the strain, epsilon is theta here. So theta is equal to stress, which is sigma, over the corresponding modulus. Here the modulus is the strain modulus. I mean shear modulus, I'm sorry. Here's a modulus is shear modulus. So sigma is going to be 5 times 10 to the power 5 Pascal, and this is in gigapascal. We can just convert that into Pascal, 10 to the 9 Pascal. So Pascal cancels out. Well, you say like there's no unit, but actually because shear strain is is an angle in radian, this will be radian. Okay, so I've got 5 over 1.2 times 10 to the power 9 and 5. This gives me minus 4 radian. So that will be the answer for the shear strain. Other strains may have just no units like this. This is just saying that this, I'm looking at an angle. You have encountered other strains, like when you're stretching a wire, we have a change in length over length, and then there is no radian there. Okay, it's not an angle, it's just a fraction. You may convert that as a percentage, but here we normally write down radian, although there is no unit. You know, ultimately it's an angle. An angle with no unit will be called radian, right? Because it's ratio of two lengths. Angle is like arc over radius. So this is an angle. If you want to think about it, it's kind of like it rotated with this radius. You know, it rotated with this radius and rotated by that much. So this angle that we're looking at, we are getting from an arc of a circle of rotation, and that's why it's radian here. Makes appropriate sense for us to write down the radian. Okay, this example, I'm done with this example. In some other video, I'm going to try to explore other types of stress and strain. Okay.